Hi, welcome to the second part of our lecture on oligopolistic market. In this part we are going to show a few selected models of oligopolistic market. First of all, output leadership, which is an oligopolistic model of market developed by Stackelberg. So we've got output leader here. This role of the leader is usually performed by the biggest firm in the market. So we've got one business that is the biggest one, the dominant firm, and others, before making their decisions, look at the leader and say, all right, let's see what the big guy is doing, and we will respond. Right? Remember, followers don't have to do the same as the leader does. They are followers in the sense that their decisions would follow, but obviously they do not have to do the same. Sometimes this leadership is assumed by the most effective business, with the lowest cost. This is, however, usually a short-term thing, because those most effective businesses over time usually become the biggest businesses, so they become dominant firms. Sometimes we also see that this leadership is assumed by a business characterized by the best market intuition. So others know our business for being really good at predicting the future in the market. And this is the situation when they say, all right, let's see what this particular business would do, because they usually know what to do. Their decisions are smart. How do we solve Stackelberg model? The idea is pretty simple, actually. Both businesses want to maximize their profit. So we will try to investigate upon that, and we will start with the decisions of the follower. Why? Because the follower is supposed to know the decisions of the leader, so their situation is less complicated. What is the profit of the follower? The profit of the follower is the difference between total revenue of the follower and total cost of the follower. This total cost depends on quantity produced by the follower, Q2. Total revenue is P times Q. So for the follower, it's the price that is in the market, P, times Q2 times the production of the follower. But the price that is in the market depends on the joint production of the first and the second player. Both leader and follower influence the price with their production, as you remember from our previous lecture. Therefore, you can see we can calculate marginal revenue here from this total revenue, and we can calculate marginal cost from the total cost. However, when we make them equal for profit maximization, you will get the equation with two variables, Q1 and Q2. Q2 is almost everywhere, Q1 appears in the price. We will not solve this equation, but we may find what is Q2 depending on Q1. So we could say we can find a reaction function. We can find a function that tells us what should be the production of the follower depending on the production of the leader. And this is kind of reasonable. Certainly, what is produced by the follower, who makes the decision as the second one, depends on the decision of the first one, what the first one decided. While we know that already, we can have a look at profit maximization of the leader. So this is profit 1, that is the difference between the total revenues of the leader and total costs of the leader. Total costs of the leader depend on Q1, production of the leader. Total revenue of the leader depends on the production of the leader, Q1, and the price from the market, which depends on the total production, Q1 and Q2. Again, we may try to find what is the profit maximization for the leader. But here we've got a nice situation, because actually when you look at this equation for profit maximization, you've got two variables, Q1 in 3 places and Q2, which appears just 1. But actually we have a way to get rid of Q2 and replace it with Q1. This is this reaction function that we found for the follower. So we take this reaction function, we put it in the equation, and here our equation becomes one single equation with one single unknown variable. So we can solve this equation and we can find Q1. If we find Q1, then we can also find Q2, putting this Q1 number into the reaction function. We know Q1, we've got Q2. Using the demand function, we can find P, which is the price. So we've got the situation solved. We know what is the total cost, we know what is the total revenue, we know what are the profits of the leader and the follower. Problem is solved. So that was output leadership, given by Stackelberg model. Price leadership. Let's take this model in a graphical way. Price leadership. So we've got the market, we've got our demand function, and we have the supply of the follower. Now what we want to do is we want to establish how much space in the market is left for the leader. We know the demand, we know the supply of the follower, and we want to know how much is left for the leader. We will find two characteristic points here. The first point will be located on the vertical axis of P, on the level of the intersection between demand and supply of the follower. For this level of price, we can see there is no room left for the leader. The whole demand is actually covered by the supply of the follower. So there is no place left for the leader. So for this P, the quantity would be 0. We need another point to determine how much space is left for the leader. Let's assume for a second, just theoretically, that the price wouldn't be here, but it would be 0. How much space for the leader is in the market if the price is 0? For the 0 price, the supply of the follower is 0. So the follower does not produce anything. The whole market is for our leader. So we've got 2 points here. We can connect them with a line. And this is what we call residual demand. This is demand for the leader's production. Residual demand is the demand that is left for the leader once the follower is already satisfied. Within this residual demand, our leader becomes a monopolist. For the leader, there is no competition in this residual demand. Therefore, we can treat this residual demand as demand for a monopolist, and then we can continue with profit maximization for monopolistic market. So what we need is, we need marginal revenue, we need marginal cost, and we make our normal considerations for profit maximization. So we look for the intersection point between marginal revenue and marginal cost. That gives us the quantity produced by the leader, and that allows us also to find the price which we find on the basis of residual demand. So our problem is partly solved. We know the production of the leader and we know the price. We know the price not only for the leader's production, but we know the price for the whole market. So let's not now forget about residual demand. Let's look at market demand. We've got the price, so we know what would be the quantity sold to the whole market. Part of this big Q is already taken by the leader. The rest is the production of the follower. We know the production of the leader, we know the production of the follower, we know the price. Problem is solved. Okay. Price and output leadership, a brief recapitulation. Those models are not universal. That means it's difficult to say in what particular situation price or output leadership may happen. Sometimes it is pretty clear. For instance, if we enter a completely new market and we build a factory there of a given capacity, and there are no rivals yet, then obviously our decision to move in to build a factory of a given capacity is output leadership situation. So we make our move, we know what would be our output. There comes some follower then who may enter the market, but they already know what is our output decision. Price leadership may be obtained by catalog publication. This is the case of Castorama, for instance, right? A well-established brand for DIY supermarkets. They publish a catalog and they put it for customers, and this is obviously a signal for local shops of the same profile, because Castorama tells them what are their prices. So obviously local shops should take those prices into consideration. I'm not trying to tell you that local shops should become or should try to be as cheap as Castorama is. No, remember that followers don't have to copy the solutions given by the leaders. No, they simply need to take them into account. So as you can see, real-life observations are actually critical in deciding which model should be adopted. The next part is on simultaneous games. So it's going to be simultaneous output setting and simultaneous price setting. Simultaneous output setting. That's a model known under the name of Cournot model, based on the assumptions that you can see here in the slide. The first two are pretty simple. The third one is a bit complicated. costless production seems to be very unrealistic. Zero marginal cost and unlimited supply seems to be very unrealistic as well. In fact, that was a certain limitation of Cournot model. Nowadays, we know how to cope with this assumption. I mean, we can give up this assumption of costless production, and we do not have to assume that this marginal cost must be zero. But today we are going to consider the original, pretty simple model made by Cournot. So we will accept this assumption on costless production and zero marginal cost. We will simply say it's not costless production, but it is without cost differences for both businesses. And zero marginal cost is a well-known example of a water producer, mineral water producer. Once you create the well and you are able to get water from underneath the surface of Earth, then actually the marginal cost of 1 liter of water is so close to zero that we can assume this is costless. Okay, so let's have a look at Cournot model, simultaneous output setting. Remember, we are going to look at this model in turns, but it's just because of the fact that when you consider your decisions in simultaneous output, you always imagine what your partner, what your rival would do. So let's have a look here. We've got market demand, which is D1, and let's think what would be the production of the first producer based on the assumption that the second one doesn't produce anything, so the production of the second one is zero. If that's the case, then the first producer is like a monopolist, so we would have this marginal revenue here, and we are looking for the intersection between marginal revenue and marginal cost. And remember, marginal cost is zero, which means the marginal cost curve is actually the horizontal line of zero. So marginal cost lies exactly on the horizontal axis of Q. So the point of intersection between marginal revenue and marginal cost is here at 480. And the price, well, the price can be found from the demand function. That's the price. So that would be the production and the price of the first producer based on the assumption that the second one does not produce anything. What would be the production of the second one? If the first one produces 480, then how much is left for the second producer? Well, it all depends on the price. It's similar to the residual demand idea that we had before. If the second one wanted to keep the price of P1, then at P1 the market would buy only 480. This 480 is already produced by the first one, so there is nothing, there is zero space for the second producer. If the price is lower, let's say if the price of the second one is zero, then they would be able to sell 480. Because the whole market is 960, the first one takes half and sells to this half at P1, so the second one could sell the remaining part, 480. Sell is perhaps not the best word, because the price would be zero, but that could be what is available for the second player at the price of 0. So the demand for the second player's production would be like D2, and then we need marginal revenue and marginal cost to find what would be the production, 240, and what would be the price. The price would be P2. So if the first one produces 480 and sells at P1, then the second one would produce 240, selling at the price of P2. Do we have our problem solved? No, not necessarily, because actually the first one produces 480 and sells at the price of P1 only if the second one doesn't produce anything. But the second one produces 240. Therefore, the production of the first one would be different. How different? We can find it from the reaction functions. Here are reaction functions of the first and of the second one. You can see how it works. Take the first equation. Q2 was believed to be 0. We assume that the second one doesn't produce anything. So Q1 was half of this big Q, half of 960, which is 480. That was the production of the first one. The production of the second one depends on the production of the first one. So Q1 was 480, this big Q, 960 minus 480 divided by 2 gives us 240, which is the production of the second one. Now you take this Q2, which is 240, you put it in the first reaction function, and you can calculate what would be Q1 now. Alright, we are not going to solve this model here with this graph, but we can try to use those functions of reaction and see where they would take us. So, let's have them. This is Q1, this is Q2. 2 dimensions, each dimension for each player. The reaction function of the first one. So that tells you how much the first one would produce depending on what the second one produces. You can see it clearly. If Q2 is 0, then Q1 would be 480. This is precisely what we had in the previous graph. The second one doesn't produce anything, the first one would produce 480. The reaction of the second one in our case is precisely the same, because these are two the same businesses without any differences in costs, remember. So it's 480 here as well, right? So that's where we start. Q2 being 0, Q1 is 480. If Q1 is 480, then from the reaction function 2, we find the production of the second one being 240. If the second one produces 240, then the first one would respond with 360. Now we take this 360, we put it in the reaction of the second one, and we learn what would be the production of the second one. As you can see, we are climbing towards a certain equilibrium, and this equilibrium will be 320 for both of players. So if the first one produces 320, the second one would respond producing 320. If the second one produces 320, the first one would respond, producing 320. We've got equilibrium here. Obviously, in Cournot models, sometimes there are differences in costs. So the market share can be different. If one business has a bigger marginal cost, the share of the market would be smaller. Sometimes the reaction functions are not simple lines, they can be curves that may, for instance, mean that there is more than one equilibrium possible. Well, things may get complicated, certainly, but the simple model of Cournot market is here, with two reaction functions, straight line, the same for each producer, and the equilibrium. Simultaneous price setting is known under the name of Bertrand model. So this is the idea that businesses sell the same product and we want them to simultaneously set the price. This is the idea of open tender, for instance. If the university wants to buy 10,000 of pens, for instance, for administration staff and professors to be able to write. Okay, so we buy 10,000 pens. And the question is, all right, we've got three businesses that could offer their production. We say, all right, so you make a proposal on your price, you put your proposal in the envelope, you send it to the university, and on one day we will open all the envelopes and we will see who proposes the smallest price. That would be the winner. Okay, so that would push those businesses to propose the lowest possible price, and obviously the lowest possible price is the price that is equal to marginal cost. So such open tender would be won by the business that has the lowest marginal cost. You can see that is a very powerful tool, because actually you can get a solution that is typical for perfect competition market, even though you have oligopolistic market. So you don't have such a fierce competition here like you have in perfect competition market, but the outcome is the same. This is why open tenders are quite often used by public institutions, including universities. The last model that we want to explain is neither simultaneous nor sequential game. This is the so-called Sweezy model. This is a kind of interesting idea. Simply imagine that you are one of the mobile operators, like let's say you're Orange, right? And the question is, if you would like to get a higher total revenue, would you increase your price or would you decrease it? The answer obviously depends on whether you believe your demand is elastic or inelastic. If you believe it is elastic, then you should lower the price and the revenue would go up. If your demand is inelastic, you should increase the price and revenue would follow, would also go up. So what would you do as the CEO of Orange? Would you reduce your price? If you reduce your price, then your competitors would quickly respond with the same move. They would reduce their prices accordingly, not to lose the customers. You can't make it secretly. If you lower the prices, you will announce it to customers, and obviously you will announce it to your rivals as well. So if you lower the price and they respond in the same way, the quantity of your customers will remain the same, whereas the price is smaller. So P is smaller, Q is the same, your total revenue went down. That would be a significant suggestion that you should increase the price. But actually, if you are the CEO of Orange and you decide to increase the price, others wouldn't follow your move, and people, your customers, would go to other mobile operators Therefore, your price would be bigger, but quantity will decrease and total revenue would decrease. So, what's the matter? Is your demand elastic or inelastic? Well, that is what Sweezy Model is about. Have a look. The idea is in the so-called kinked demand curve. Your demand is in some sense elastic and in some sense it is inelastic. It depends on whether you increase or decrease your price. So in fact your demand is made of two different demands. If you want to increase your price, your demand is pretty elastic. When you want to decrease it, it's pretty inelastic. A kinked demand curve. Now, if you have those two parts of your demand curve, then you can also see the marginal revenue that is not a line, a single line, but actually it is composed of two parts. The first one, this marginal revenue, is the product of D1, and the second marginal revenue is the product of D2. As you can see, there is a gap here, and if your marginal cost is located in this gap, then you will be tempted to produce in the E point, meaning you will produce this quantity and you will produce this price here. What is funny about the Sweezy model is the fact that even if marginal cost changes somewhat, it doesn't have to mean that you need to change your production. Have a look. Marginal cost may shift a little bit to the left, and still you don't have to change your production. Actually, if you would like to change your production, you will deteriorate your profit. So Sweezy model is about changes of cost within some range that does not influence market prices and output. You can see it when you look at petrol stations, for instance. You know, the volatility of oil prices is very high. So marginal cost of car fuel production changes quite often, and prices in petrol stations, they do not change every hour, they do not change every day, they change from time to time. So as you can see, when marginal cost of fuel production fluctuates in this gap here, it does not send any incentive to change the price of the fuel. Only if this marginal cost goes up, starts to intersect with the upper part of marginal revenue, or if it goes down and starts to intersect with this lower part of marginal revenue, then you react, changing your production and changing your price. The last thing that we want to talk about in the context of oligopolistic market is monopolistic collusion. This is not actually a model. It's the idea that sometimes market participants may say, all right, why would we actually have to compete against each other? We can share the market. We can perceive ourselves as monopolists. We together, we can produce QM and we can maximize our profit by setting the price at this level. So actually that would be our cost, average cost, and this triangle here is the profit. So if there are, for instance, two participants, two market players, they could simply split the market and have half of the cost, half of the revenue and half of the profit. So we divide the monopolistic profit between two businesses, let's say in the equal way. Obviously, in the real life, the problem would be how to divide market shares, whether it should be equal or unequal. Everyone would have probably their own idea about how it should be done. Monopolistic collusion, remember, would give the opportunity of gaining the highest profits for the members of this collusion. So that would be about actually reducing the output and pushing the price up. That allows to get high level of revenues and therefore high levels of profits. Remember, and the monopolistic collusion, it is very tempting to cheat. I mean, if we make collusion and we make the kind of agreement that we will limit our output to push the price up, then it may be pretty tempting to me not to decrease my output, benefit from your reduction of the output, in the sense that you, by decreasing your output, you will push the price up and I will not change my output and I will get additional money from that. Collusion creates temptation to cheat, and the thing is as simple as this. If other participants are honest, then if you cheat, that might be very profitable for you. If others are cheaters, then it is just necessary for you to cheat as well, otherwise you will not survive. So to keep the collusion effective, there must be some mechanism to control whether someone is complying with the agreement or not, and there should be some possibilities for others to punish the cheater. Otherwise, the monopolistic collusion wouldn't work. Actually, punishment is not necessary if the threat of punishment is credible. In other words, if the market participant know that others may punish him for cheating, they wouldn't cheat. Collusion is illegal, but remember, it all depends on the context. I mean, if you look at OPEC, for instance, Organization of Petroleum Exporting Countries, this is a classical collusion, and no one can do anything about it. Simply, they are too powerful. And this is a brilliant case of collusion. You can trace some news on how they set limits, how they make agreements to cut down production to push the prices up. The last element of oligopolistic market considerations is innovativeness of oligopoly. Remember, oligopolistic markets are believed to be one of the most innovative markets. Oligopolistic players are able to have high profits and they spend a lot of money on research and development activities. Therefore, you can see great progress in those industries which are formed as oligopolistic markets. Look, for instance, at pharmaceutical industries, or look at mobile industry or electronics. They show you how efficient, how innovative oligopolistic markets can be. Patent protections are very important elements because they allow those oligopolistic businesses to gain benefits from the innovations they work in thanks to their R&D activities. All right, that is all about oligopolistic market. I hope you liked that. Leave some comments if you have one. Give me a like if you liked that. Thank you very much for your attention. Bye.